Academy Foundation presents the special case explaining the relationship between space-time reference frames and the continuity of the laws of physics. In this presentation, we will examine how space-time is constructed and conserved. One day, Einstein envisioned his trolley accelerating away from the clock tower in Bern. As he approached the speed of light, the hands on the clock moved faster, while those on his watch showed a different reference frame. The effect on space is scaling. Let us call these two reference frames 4-scale and 2-scale. It is as if we switched from using a metric ruler to a standard ruler. The object being measured did not change. Only the scale on the ruler used to apply light constants changed. Directionally shaped scaling is how fields like gravity work. Scaling also affects the absorption spectrum, redshift, and direction of light. Let's address the bad hair questions. How in science did Einstein come to this? And what are space and time anyway? Space is generally defined in Clarke's terms as continuous and available. What about Leibniz's discrete things? Everything has its own space. Discrete spaces are easy to imagine because they regulate themselves as we expect. The lady in the middle has her own space. Don't mess with it. She's tougher than she looks. The group collectively has its own space. This space is the people, their activity, and the moment in time separating them. The volume of action and related lengths of time are latent, meaning they are opportunities. The first law defines perspectives for discrete things and shows energy translates directly into kinematics and space-time. The unit U in context is a dependent variable. It increases or decreases as increments of energy are added or removed. The proportional increments affecting how much energy added translates into work dependent on how the energy distributes out of context. In the out-of-context perspective, du and the details of distribution are independent variables, making du the scaling factor for differentiation. The details of distribution among kinetic and discrete variables is information. The combination guarantees a degree of inefficiency always applies. In this picture, Einstein, Lorentz, and Earth are clearly discrete spaces. Aside from them are the latent spaces we see as the black background emission can act on, and the grid shaping a directional density. Light is the obvious form of dynamic latent space. In this picture are dynamic spaces. Each consists of information mixed in a way that works in a change process. Change processes are enabled by static opportunity. Standing energy in thermodynamics is background temperature and pressure. Free space is the static byproduct of the spherical wavefronts of CMB. For light, spherical wavefronts are standing waves with energy approaching the minimum frequency. There is no pure vacuum. Values create an uncountable mixture of independent, irregular points defining only parts of spacetime. It is not discrete as Leybourn's ether theory suggests. The points have no control individually or together, but they can and do get focused to perturb matter. Neutrinos perturb from the slightest mixing of free space. By standing, free space acts like the tracks of Leybourn's roller relative to light. The absorption pattern in the emission of light provides a shape to follow those tracks. This is the mechanism behind Euler's solution to D'Alembert's wave equation, the first solution for flat space-time. Free space enables the propagation of light and adds a subtle twist that transforms its nature. Ultraviolet light is focused pressure transforming into volume. At green in the optical spectrum, that reverses to unfolding volume, transforming into enfolding pressure. As unfolding volume, light is giving space a bulk value, like the weft in a fabric. The twisting and stretching transforms the volume into a straight line of warp. giving priority to the absorption value representing the enfolding pressure of time. Time is flux resistance to change, appearing here as the weave of weft into warp. Warp is attached to the loom and stretched. The loom of the universe is the unfolding of temporal volume by discrete spaces breaking down. Discrete spaces dynamically build up to degenerate density points, geometrize, compound, and then systematically reverse the process in variable roles also. Here, an artist depicts walls and clusters of galaxies flowing as filaments. Their action is unfolding the volume of time, separating them, stretching the warp. The goal of general relativity was to prove the special case in classical terms, which is done by the stress-energy function. If we instead slow down a little to see what the variables are doing concretely, we also get to see how virtual matter is constructed. Hypersphere concepts are vital to understanding how gravity, entropy, and singularities work. Pressure is measured in kilograms per meter second squared. It is a zero-sphere linear measure of space called a hypersurface in one-sphere context. It is only part of a complete space. As a two-dimensional hypersurface under the right conditions, it is an event horizon. Under those same conditions, value added into the potential volume of that space is confined to a Schwarzschild radius. A two-sphere application is like filling a balloon. The linear value can also be applied to a volume called a Ricci, which is distinct from the surface. The balloon with distinct volume is the three-sphere. Mixing the two spatial qualities is called gloaming in mathematics. The degree of gloaming depends on how small we scale the virtual division of that space into points. Einstein's geodesic field equation provides a simple way to show hypersphere assembly. Einstein shows the pressure as a scalar labeled r. Scalars are without shape, so he applies the metric scalar to first define it as a surface, using G for geode. The volume symmetry has half the radius of the circular surface applied to it. R consists of information, part of which defines a surface. The other part applies directly to the symmetry as the Ricci volume. The hypersurface is then kinetically applied to the volume. Kinetics is the study of motion. In this case, it is the motion relating axes of space consistent with mixing. Mixing creates surface gravity as a dilation gradient between the two manifolds. It also creates a degree of displacement in free space which defines microgravity around the object and the ranged effect of mass in orbital mechanics. Einstein's cosmological constant is the scalar effect of the environment. Chromodynamics with complex operators evolving into octonions is an entirely separate subject. What we need here is to acknowledge two details. First, they are change functions that control how spaces are shaped, given direction, and otherwise function. Second, to be functional, a change function needs opposite features, proportions, and basic rules of logic. All the change functions derive from the Boolean-defined j and I. Their squares are -1, and the squares of their chirals are +1. This is done by giving each operator two spaces, one volume and one pressure, one angular and one linear, one contracting and one expanding. And these are either stacked sequentially or simultaneously happen together. Time depends on change transformation, which themselves depend on spatial transformations driven by distribution. This links the variables to space-time constants. The space-time constants describe how values act on space, how space responds to that action, and the relationship between the linear and angular forms of value. The space-time constants of light are angular, its magnetic inverse, and Planck's spin. These and the speed of light do not change between frames of reference. Static values are isolated into one category. Dynamic values combine linear and angular axes into a spin axis. The relationship between the axes is kinetic rotation. Newton's constant isn't quite constant. The variation is the angle of rotation mixing the angular into linear axes, shown here as phi. It is also known as the Cabebo or Weinberg-Weak mixing angle. Dilation exaggerates the angle hyperbolically, linking time to mass and gravity. Degenerate densities are one of three general static forms of discrete spaces. Discrete spaces first fill a hypersurface or volume with emission or absorption value, then combine those two spaces into a distribution. In a degenerate density like a proton, neutron, nuclide, or neutron star at the center of a pulsar, these spaces are fully occupied. Any additional value, like the details of distribution, becomes a forced variable projected around the object. The field equations show how all three static forms of discrete spaces relate to each other and the spacetime constants. Anything additional to the constant of identity can conditionally be emitted or excluded, as with the pulsar above. If the space is shaped to contain emission, as with a singularity, then it has to fill until the whole extra value gets excluded. These energy changes are dynamic uses of discrete spaces that will cause matter to transform. With our improved understanding, we can now see how Galileo's observed distortions in length between reference frames are proportional to a change in scaling that causes emission, like particle beams. We can further understand how redshift at close range with Doppler radar reflects direction and velocity, but past z equals 1, the distance and time makes motion indiscernible. If we pay close attention, we can see how simple virtual particles, up through leptons, are perturbed by one stream of information. That triangulation provides acute, right, or obtuse mixing angles that classify particles, showing how changes in dilation cause identity changes called oscillation. Einstein's conserved static universe model is as accessible as understanding how special relativity works in nature's terms. That understanding reaches into every aspect of physics. Then we listen to these two guys. While trying to understand how atoms exhibit contradictory mechanisms and qualities, they realize that physics is not a science of exclusion. Every valid solution for a complex applies in degrees relative to its boundaries. That is the Copenhagen interpretation that defines quantum mechanics. The universe is complex. It doesn't fit in just one simple solution. Understanding the special case gives us the tools to show how the solutions can be put together to complement each other. It is a universe of interacting galactic Big Bang processes, distributed like people at different ages and stages of development without beginning or end. A closed universe of discrete transformations and interactions. The changes in distribution are stories, unfolding perpetually in our telescopes. We've only scratched the surface of special relativity here. Quantum relativity keeps digging even deeper into the special, latent, discrete, and distributive cases. Quantum relativity conceptualizes advanced topics in established physics to provide educational and practical tools. Our biggest problems in physics are human, specifically too much information and no accurate standardization of the concepts. Basically, advanced physics needs an introductory class to put it all together. Remember to subscribe and stay tuned for other educational videos. Thank you.